Bühler Motor fractional horsepower DC motors. Application engineering. This sequence of training sessions will explain in detail the practice of application engineering, which means using existing motors and adjust them by winding changes to meet the performance requirements. Hello, my name is Gerhard Hofmann. In this first training session, I will show you how to find an existing motor that will meet the requirements of a specific application. The first and essential question to be clarified is what the application is. The more familiar you are with the application, the easier it is to qualify the motor. After the basic knowledge of the application, the main parameters must be known. It is the load point, which will basically define the performance curve, and the voltage at which the motor will be operated. If we recall the basic training sessions, we know that the load point is the motor speed at a certain torque load. For a first and basic selection of a motor, the knowledge of the load point is sufficient. We remember from the basic training how a performance curve of a permanent magnet DC motor looks like. Step by step, we can now build up this performance curve, starting with the known load point. For this, we need the speed versus torque curve first. Entering the load point allows us to draw a straight line through this point, and we get n sub 1 and t sub 1, which would lead us to the speed regulation constant r sub m1. As only one point on a straight line does not describe the line completely, we could also draw a line that would lead us to n sub 2 and t sub 2. The speed regulation constant r sub m2 would be the consequence. Both straight lines meet the load point. The blue line is representing motor 1, which is a much bigger motor than motor number 2, represented by the red line. From this we can see that the knowledge of the load point only does not help to define the motor we need. What we need is a second point on the straight line. This second point could be the stall torque, T sub S. With the knowledge of T sub S, we have all informations to calculate the speed regulation constant of the motor we need. How can we determine T sub S now? For this, we need to know the application conditions. Basically, the complete performance curve is always in the back of our mind. If we have an application with continuous operation conditions, we want to have the load point in the area of the maximum efficiency, which means T sub L should be approximately 10 to 20% of T sub S. In case of a cycle operation with short on times, the load point may even be up to the maximum output power, which means T sub L may be up to 50% of T sub S. With the definition of T sub S, there are 2 points now which perfectly describe a straight line. The slope of this straight line is the speed regulation constant R sub m. With the calculated R sub m, a motor out of the existing portfolio may be chosen. If we look at the data sheet of the motors, we can see the speed regulation constant here. It is a constant for a specific motor type and will not change even if we modify the motor winding, assuming we keep the copper filling in the armature constant. Looking at the full set of data of a chosen motor, there are values which will not change by winding or voltage changes. Starting with R sub m, as mentioned before, also weight and rotor inertia, as well as thermal resistance, thermal time constant, and axial play will not change. With this chosen motor, a lot of parameters are fixed now, as the motor is already existing. It has to be checked now whether the main dimensions of the motor fit the application mechanically. Flexible parameters like shaft extension, shaft configuration, cable length, brush grade, RFI components and armature winding may be adjusted to meet the application requirements perfectly. No-load speed and sub-zero can now be calculated using the formula shown here. And sub-zero does not really have a practical use, but it is necessary for further calculations, which we will see later. As the chosen motor has a more or less fixed design, the no-load current I sub-zero may be taken from the datasheet. If the current I sub L is given by the application, the second point on a straight line is known. With this information, the current versus torque curve can be drawn now, and KT may be calculated. Shown here is the current versus torque curve and the formula to calculate K sub T. With the so far derived data, the motor is defined completely. Any load point on the performance curve can be calculated now with the following formulas. Load speed N sub L equals no load speed N sub 0 minus speed regulation constant R sub M multiplied by the torque load T sub L. Load current I sub L may be calculated by I sub L equals to no load current I sub 0 plus 1 divided by KT multiplied by the torque load T sub L. An important reminder for all further considerations is that the speed regulation constant value Rm will not change with winding changes in the armature if the copper filling stays constant. Torque constant value Kt on the other hand side will change with winding changes proportional to the number of turns per coil. I will close this first chapter by a practical example. It will show you in real numbers how the application engineering based on the theoretical learning content works. The example may be an application in a general industries product where the motor has to drive a load of 10 Newton centimeters at a speed of 5000 RPM. The drive mode is continuous operation for 1 hour per day. The operating voltage is 24 volts DC. The load point we see here is T sub L 10 Newton centimeters and N sub L 5000 RPM. From the power supply we know that the maximum continuous current is 3 amps. As we know that we have a continuous operation and we know that the torque load should be in the area of 10 to 20% of the stall torque, we chose 15% for the torque load, and this means that stall torque would be 67 Newton centimeters. Again, the complete performance curve looks like this. If we draw our 10 Newton centimeter load point, the 67 Newton centimeter stall torque, we can calculate the speed regulation constant, which results in a value of 88 rounds per minute divided by Newton centimeter. The Rm value of the selected motor must be equal or smaller than the calculated value. So our catalog search shows that the 1.13.044.236 motor comes close to this value. The 1.13.044.236 has an R sub M of 63 rounds per minute per Newton centimeter, which is smaller than our calculated value of 88 RPM per Newton centimeter. If we check the torque constant K sub T now, the K sub T value of the selected motor should be equal or greater than the calculated value. Our calculated value, shown here, K sub t is the torque T sub L divided by the difference of the load current minus the no load current, and this results in 3.5 Newton centimeters per amp. The 1.13044-236 motor has a K sub T of 5.3 Newton centimeters per amp, which is greater than the calculated value of 3.5 Newton centimeters per amp. Calculation of no load speed and stall torque considering the actual values of R sub m from the selected motor 1.13044-236 shows a no load speed of 5,630 rpm. From the relation of no load speed divided by stall torque being R sub m, we can change this into the calculation for the stall torque being no load speed divided by R sub m. We result in a stall torque of 89.4 Newton centimeter. The calculation of the stall current using the calculated value of K sub t shows that our stall current would be 25.7 amps. Here we can see the performance curve of our target motor based on the parameters of the selected motor 1.13044-236. Within the next session, I will show you what has to be done to modify the selected motor 1.13044-236 to meet the target performance curve exactly.